introduce Qinghua Liu. Qinghua is a PhD candidate at Princeton with Qi. He is working on reinforcement learning theory, and he has a couple of very impressive papers on various topics like multi-agent learning and POMDPs. And today he is talking about optimistic algorithms for partially observable environments. So with that, the stage is yours.
Thank you for the nice introduction. And I want to thank our organizers for restarting this great seminar and for inviting me to present one of my favorite works. And I'm Qinghua from Princeton. And as this title suggested, today I will talk about optimistic maximum likelihood estimation, a simple and generic algorithm for reinforcement learning. And this talk will be based on joint works with my co-authors, Alan from Harvard, Pernice from Google, Chava from U Alberta and DeepMind, and Qi from Princeton. So we all know reinforcement learning has achieved huge empirical success in all kinds of applications. It has been applied to train superhuman AI agents that can play Go, play chess, play Texas Hold'em poker. People also use it in robotics to teach robots to play, to perform all kinds of very challenging tasks. For example, in this image, OpenAI trained a robot that can play Rubik's Cube. Now so to begin with, let's first define what is reinforcement learning. So in reinforcement learning, there are two key components. The first one is the learner, and the second one is the environment, parameterized by some parameter theta star. The learner interacts with the environment in the form of episode. And formally, each episode consists of capital H stages. At each stage, small h, the environment first samples an observation, OH, from this conditional distribution, P theta star, conditioning on all the observations and actions that have been seen in the current episode. And then the learner observes this observation, OH, and takes action, AH. We repeat this process for capital H stages, and after that, the learner receives a reward, R, which is a function of all the observations and actions that have been seen in this episode. And then this episode terminates. And we call such one episode of interaction one sample. So in short, one sample consists of capital H pairs of observation and action. And to study reinforcement learning, we need to first introduce several very important terminologies. The first one is policy. So mathematically, policy is a set of functions that maps a sequence of observations and actions to a distribution over action space. So intuitively, it specifies how to pick actions, conditioning on your current conditioning on the observations and actions that you have seen in the current episode. And given a policy pi, we can define its value, V pi, which is equal to the expected reward the learner will receive if she follows policy pi to sample an episode. And the objective of reinforcement learning is to find a good policy pi hat such that the value of pi hat is at most epsilon smaller than the optimal value. So here, the optimal value is the maximum value that can be achieved by any policy pi. And in this talk, we will focus on the practical learning from interaction setting. So we will assume the environment parameter, this theta star, is unknown to the learner. And we want to find a good policy pi hat solely by interacting with the environment. In other words, we don't assume access to any simulator. And to simplify a presentation, in this talk, we will assume the reward function R is known to the learner. So any question about the setting of reinforcement learning? So by the way, if you have any questions, so feel free to interrupt me and I'll post it in the chat. And so in reinforcement learning,
maybe one quick question.
Mm-hmm.
So this reward function, is it like a cumulative reward, or it doesn't really matter?
Oh, so here we are defining everything in the most general form. We can so if it's a summation of ROH-AH, it's also a special case of the current definition. So it can be cumulative reward.
And there's a question about the observation space. Is it continuous or discrete?
So in our later slides, we will show we can handle continuous observation for some special class of POM-DPs. So for now, we can assume it can be discrete or continuous. It can be arbitrary. So our results can apply to continuous observation space.
And finite actions?
Oh, finite actions, yeah. Finite actions, but the observation space can be continuous. Okay, any other question? Okay, let's move on. So in reinforcement learning, we care about two types of efficiency. The first one is statistical efficiency or sample efficiency. So it basically measures how many samples or how many interactions with the environment we need in order to identify a good policy. And the reason we care about this statistical efficiency is that collecting samples can be super expensive and time-consuming. So for example, if you are collecting samples for robotics task, collecting one sample might take 30 seconds. And we might need more than 1 million samples to solve the task of interest. So this procedure can be super expensive and time-consuming. And the second one is computational efficiency. It measures how much additional computation we need to perform in order to extract a good policy from the collected samples. And in this talk, we will focus on the statistical efficiency. And in the following slides, I will introduce you a simple and generic algorithm called optimistic MLE. And we will show this algorithm is super simple and it can be used to solve a large family of IO problems using only polynomial samples. So this algorithm builds upon two simple ideas. The first one is optimism in the face of uncertainty. So what does it mean? So given a set of possible hypotheses about the world, we should make our decision based on the most optimistic one. Let me explain this abstract concept by using a concrete example. So let's imagine you are in a casino and you are playing some gambling machine. And on this gambling machine, there are D arms, A1 to AD. And there is an unknown parameter, theta star, that lies in the D-dimensional unit cube. Each time we pull arm AI, we will receive a reward sampled from a Gaussian distribution centered at theta I star. So in short, for each arm, there is an unknown reward parameter, theta I star. And when you pull this arm, you receive some reward, which is equal to theta I star in expectation. And the problem is, suppose we are allowed to play this multi-arm bandits for T rounds. how should we pull arms adaptively based on previous reward feedback to achieve high total reward? So here our superscript T denotes the reward we receive in the Tth round of arm pulling. It turns out we can solve this problem by using optimism. So and the solution is very clean. Specifically, in the case round of arm pulling, we will construct a confidence interval Li/Ui for each arm Ai using the previous reward feedback. And we want this confidence interval to contain the true reward parameter theta I star with high probability for each arm Ai. So like, for example, in this figure, we can see the confidence interval for arm A1 is 0.1 to 0.9, and the confidence intervals for other arms is 0.6 to 0.8. And then we will pull arm greedily by only looking at the upper confidence bound of each arm. And in this case, arm A1 has the highest upper confidence bound, 0.9. So we will pull arm A1. So in short, we can solve this problem by pulling arm greedily with respect to the upper confidence bound. And we can generalize this idea to reinforcement learning. And we define V pi theta to be the value of policy pi in an environment parameterized by parameter theta. In each iteration, optimistic MLE performs 3 steps. First, optimistic MLE constructs a confidence set B such that the ground truth environment parameter theta star lies inside this confidence set with high probability. Second, given this confidence set B, we compute the upper confidence bound for the value of each policy pi, and then we pick a policy pi k to be the policy with the highest upper confidence bound. And after that, we execute this policy pi k to collect new samples. And we repeat this process for capital K episodes. And finally, we output the uniform mixture of all the policies we have executed. So this is the algorithm. So the only piece that is missing here is how we construct this confidence set B using the collected data. And we do so by relaxing the classic MLE method. Recall the classic MLE method. Given a dataset D, MLE computes the parameter candidate that has the highest likelihood on dataset D. And we construct our confidence set B by relaxing MLE a little bit. Specifically, we construct our confidence set B to include all the parameter candidates theta whose log likelihood on dataset D is at most beta smaller than the maximal log likelihood. So this is the maximal log likelihood that can be achieved by any parameter. And this is the log likelihood of parameter theta. And this parameter beta measures the degree of relaxation. And as a special case, when we pick beta to be 0, this confidence set B will collapse to the solution set of MLE. And by putting all pieces together, we get the complete version of optimistic MLE. So first, we use relaxed MLE to construct confidence set B. And then given this confidence set B that contains the true parameter with high probability, we evaluate each policy optimistically and pick the policy with the highest upper confidence bound. And after that, we execute this policy pi_k to collect new data. And we repeat this process again and again. And finally, we output the mixture of all the policies we have executed. So this is the full algorithm of optimistic MLE. So any question about the algorithm?
I guess you will explain later how beta is going to be chosen?
Sorry, can you repeat?
You will explain how beta will be chosen?
Yes. So you mean this capital beta? Or this?
The beta, the relaxation parameter.
Oh, this beta. Oh, yeah. Sorry. So beta will be roughly log cardinality of this parameter space theta.
So theta is finite or countable, or what's the?
Oh, so if theta is okay. So if this parameter space capital theta is finite, we can pick this beta to be roughly log cardinality of theta. And if theta is infinitely large, we will pick beta to be roughly of order log bracketing number of theta.
Gotcha.
So
like a covering number kind of thing, right?
Yeah, it's like covering number. Yeah. So how is this relaxation helping? Okay. So let's go back to the original MLE approach. So the original MLE method picks a single point estimate, theta height. And in most cases, with high probability, this theta height will not equal to your ground truth parameter, theta star. However, if we relax MLE a little bit by defining our confidence set in this way, we can prove with high probability the ground truth parameter theta star will lie inside this confidence set B. And if this confidence set B contains the ground truth parameter theta star, we can guarantee optimism. Because if the true parameter theta star is not inside your confidence set, it's impossible for you to construct a feasible confidence interval for each policy. Any other question? Okay, then let's move on. Okay, now we have an algorithm. We want to see what kind of problems we can solve by using this algorithm. And in our work, we prove that we can use optimistic MLE to solve a rich family of our problems within polynomial samples. Such problems include fully observable IO problems like tabular MDP, factored MDP, kernel linear MDP, sparse linear bandits, and all other problems of low witness rank. And we can also use it to solve problems with partial observability, like observable POM-DPs, decodable POM-DP, and well-conditioned PSRs, etc. And now let's start with POM-DP.
So just a quick question. What do you mean by solves in this table?
By solves, I mean if we run optimistic MLE on this problem, we can learn a good policy within polynomial number of episodes.
I see.
So we only look at the statistical efficiency here. So
Gotcha.
The computation might be hard.
Maybe we can return to this in the end, but I guess I have in my head that for sparse linear bandits, maybe you need some type of exploration which is not optimistic to get an optimal rate.
Okay, so actually I we can get the optimal rate for sparse linear bandits in this case.
Okay.
But up to logarithmic terms. So we can
Yeah, the
get
logs
like
I'm fine.
square root. Yeah.
Okay, let's return to this at the end. I'm curious how this works.
Okay. Okay, so so let's start with POMDP. So POMDP can be viewed as some combination of MDP and hidden macro model. So in POMDP, we have some hidden state structure. So in each episode, the environment will first sample a hidden state S1 from the initial state distribution mu1. And then the learner will observe an observation O1 that is sampled from the emission distribution of O1. After that, the learner will pick some action A1, and the environment will transition to another hidden state S2 that is sampled from the transitional distribution T, conditioning on the current hidden state S1 and the current action A1. And we repeat this process for capital H stages. And specifically at step small h, we first the learner observes some observation OH samples from the emission distribution of SH, which is the current hidden state. And then the learner picks action AH. The environment transitions to another hidden state, SH plus 1, that is sampled from this transition distribution, conditioning on SH and AH. And finally, after the learner observes O capital H, the current episode terminates. So in short, a POMDP is parameterized by three components. The first one is the initial distribution over hidden states. The second one is the emission kernel, and the third one is the transition kernel. And most importantly, in POMDPs, the states are always hidden from the learner. It has been known that learning POMDPs without any assumption is statistically intractable in the worst case. So what do I mean? So it basically says if you don't make any assumption about POMDPs, you will need exponentially many samples to learn a good policy. So let me explain this harness result by using a toy example. Is it possible to work with the belief state instead of tracking history during current episode? Oh, okay. So if you know the initial distribution mu1, so here there is a question by Rahul. He asks, is it possible to work with the belief state instead of tracking history during current episode? So if you know the initial distribution mu1 on the emission kernel O and the transition kernel T, you can definitely track the belief state. But here we assume all the parameters of POMDP is unknown. So you can't you can't compute the belief state because you don't know these parameters. Okay, let's go back to this example to explain why learning POMDP is hard. So in this POMDP, there are two states, a good state SG and a bad state SB. And these two states have the same emission distribution. In other words, no matter what's the current hidden state, you always observe the same emission. And we define the transition dynamics in the following way. In each episode, we always start from the good state. And there is a special action sequence A1 star to capital H minus 1 star, such that at each step H, if we take the special action H star at the good state, we will stay in the good state. Otherwise, we will transition to the bad state. And once we transition to the bad state, we will stay there forever. So no matter what actions we take, we will always stay there. And we define the reward function so that the learner receives reward 1 if and only if she stays at the good state in the final stage. So in this problem, in order to receive reward 1, the learner has to take the special action correctly at each step H. And if she takes 1 step wrong action, she will transition to the bad state and receive nothing. So the optimal policy is to take each special action 1 by 1. However, in order to identify this special action sequence, we basically need to try all the possibilities. So in the worst case, we need exponentially many samples to identify this special action sequence. In other words, to identify the optimal policy. So why this instance is hard? Because the observations reveals no information about the hidden states. We can easily generalize this hard instance to show that if there are two state distributions that have the same observation distribution, then learning problem DP is hard. So mathematically, if there exist two state distributions, mu1 and mu2, these two state distributions, mu1 and mu2, are not equal, but their induced emission distributions are the same, then learning problem DP is hard. So any question about this hard instance?
Not so much the instance, I guess, but this claim that if there are two states with the same emission dynamics, then it's hard. Can you say what that means exactly? It means you can always construct a reward and transition such that it's like this hard, or?
Oh, so I mean, so if the observation, okay, so given an, okay, so mathematically, so given an observation kernel, if it's possible for us to, if there exists two state distributions, nu1 and nu2, such that nu1 is not equal to nu2, but the induced observation distribution of nu1 and nu2 are equal, then we can construct some transition kernel and reward function such that learning this problem DP is hard.
Gotcha. I see. And I guess in the example before, the important thing is you just can't see the state ever.
Yeah, because the observations are completely informative.
Yeah, uninformative.
So there's no uninformative. There's no useful information.
Yeah.
Okay, so let's move on. So as we just discussed, when the observation distribution reveals no information about the hidden state, learning problem DP is statistically intractable in the worst case. So in order to get rid of these such pathological examples, we need to introduce some condition to make sure that observations are informative. And the condition we consider here is called alpha observable condition. It says that for any two state distribution, nu and nu prime, the distance between their induced observation distribution is lower bounded by alpha times the distance between these two state distributions. So by introducing this condition, we can guarantee different state distributions will induce different observation distributions. And as a result, we can get rid of the previous pathological examples. And by using and by assuming this alpha observable condition, in 2020, with Akshay, Sham, and Chi, we proved the first polynomial sample complexity guarantee for learning POM-DP by using the method of moments. However, this method is rather complicated and do not easily generalize to other subclass of POM-DPs. So last year, with Chaba, Allen, and Chi, we proposed the optimistic MLE algorithm and proved that it has polynomial sample complexity guarantee for learning tabular observable POM-DPs. And later on, we further improved the guarantee for OMLE. And with Pernice, Chaba, and Chi, we proved that OMLE can also learn POM-DPs with continuous observation space. And to our knowledge, this is like the first line of works addressing the statistical efficiency of POM-DPs under a clean condition. So now let me formally state what guarantees we have for learning observable POM-DPs. So we can prove that optimistic MLE can learn an epsilon optimal policy for alpha observable POM-DPs within this number of episodes. So here, capital S is the number of states, capital A is the number of actions, H is the length of horizon, and N theta is the bracketing number of parameter space theta, and alpha is the observable parameter, and this epsilon is the suboptimality parameter. So importantly, the above theorem applies to POM-DPs with continuous observation space. So let me give you a toy example. So this example is named MDP with Gaussian observation. It's a very artificial one. So assume we have a tabular MDP, and however, at each state, we cannot directly observe which state we are at. We can only observe an observation emitted from a Gaussian distribution centered at ES. So this ES is a one-hot vector. All the entries except the entry at position S are all 0. So basically, it's it's the standard basis. So this is one toy example with continuous observation space. And we also have similar results for the multi-step extension of observable POM-DP. So in the previous slides, as you can, so in order to guarantee this observable condition, we need to require the number of observations is at least as large as the number of states. And in our later works, we extend our, we relax this condition a little bit by allowing the observation space to be smaller than the state space. So it's some extension. Okay, this is the result for observable POM-DPs. Is there any question? Oh, by the way, previously there is a question asking whether the observation space can be continuous. And here, we allow the observation space to be continuous. Okay, if there is no question, let's move talk.
Just the distance is the total variation distance, right? In the previous slide, I guess.
Yeah, TV distance.
Is this super significant? Of course, in the finite case, it doesn't matter much, but in the infinite case, maybe it matters a bit. Is it important?
Why it matters in the infinite case?
I think guess because the topologies could be different.
I see. Okay. So I think in this world, we only consider a case where where this TV distance is well defined. But I guess it might be possible to extend this condition by replacing this like TV distance by Heidegger distance or other probabilistic distance. I think it might be possible, but I'm not 100% sure.
Cool, thanks.
Okay. And the second example we consider here is decodable POM-DP. So in short, we say a POM-DP is decodable if the M-step recent observations and actions decode the hidden state. So let me explain this by using an example. So let's consider Super Mario. So when we play this game, if we only at each time t, we can observe an image of the current game state. However, this doesn't give us the complete information about the game. For example, the velocity of Mario. We cannot compute the velocity of Mario from a single image. However, if we use several very recent images of the game, we can accurately compute the velocity of Mario. And we prove that optimistic MLE can run a good policy for M-step decodable POM-DPs within this number of episodes. So here, D denotes the dimension of certain system dynamics matrix. We will explain the definition in the next slide. And A is the number of actions. So we have exponential dependence on this small m. And H is the length of horizon. And similarly, n theta is the bracketing number, and epsilon is the accuracy parameter. And it has been shown that this exponential dependence on m is inevitable. And importantly, this theorem also applies to POM-DPs with continuous observation and continuous action and continuous state space. And now let me introduce what's the dimension of system dynamics matrix. Okay. Let's consider a general sequential decision-making problem. And we define a system dynamics matrix at step H as following. So let's imagine there is a huge matrix. Each row corresponds to a possible history, and each column corresponds to a possible future. So here, O1, so this is history, this is future. And we define the entry at position here to be the probability of observing O1 to O capital H, conditioning on your action sequence A1 to A capital H. So this is a system dynamics matrix. And we say, okay. And the system and the D system here is simply the rank of this huge system dynamics matrix. Okay. And now let's consider a more general setting. So now I want to, so because previously we talked about decodable POM DPs, observable POM DPs. And now I want to unify these two subclasses of POM DPs into one single setting. And the way we unify it is to use this system dynamics matrix. We assume this system dynamics matrix MH is rank D and gamma well condition. So this is kind of this is like an informal assumption. And we can show for observable POM DPs and decodable POM DPs, they all satisfy this assumption with moderate rank D and condition number gamma. And we can prove that for any sequential decision-making problems that satisfy this assumption, optimistic MLE can learn a good policy within this number of samples. And here D is the rank of the system dynamics matrix, and gamma is like the condition number of this matrix. And all other parameters have the same definition as before. So is there any question about this slide? So basically here we're introducing a general condition that can encompass observable POM DPs and decodable POM DPs.
Will you say a little bit later what this gamma well-conditioned thing means?
Oh, so it basically, okay. So when we say a matrix is low rank, it means that there exists several columns of this matrix, such that we can use these columns to represent all other columns in the matrix, right? And this gamma well condition basically means when we represent other columns using these D linearly independent columns, the coefficients will not be too large.
I see.
So intuitively, that's what gamma well condition means. But the accurate definition might be will be slightly different. But the key idea is roughly what I just described.
So maybe one quick question. Do we know what the rank is for very simple models like, say, linear bandits, for example?
For linear bandits, okay, let me see. Okay, so for linear bandits, I think the rank is the dimension is equal to the dimension. But you need to first reduce. Okay, so one thing I want to mention. So here we are assuming the reward function is known. So if you want to write linear bandits as a special case of our setting, you need to first make it an MDP. And then you can encode the reward information in the transition dynamics of that MDP. And then you can show the system dynamics matrix of that MDP has low rank.
Okay.
I also want to remark that there are several concurrent works on learning low-rank sequential decision-making problems. And they get similar results under some similar assumptions. Okay. So as I mentioned before, we can prove OMLE provably solve a large family of IO problems. And these problems include both fully observable and partially observable problems. And in order to analyze all these problems in a unified framework, we introduce a general condition called Thiel condition. So this is gonna be a little bit technical. So, okay, so we say a model class theta satisfies Thiel condition if there exist two sets of feature mappings, Fi and Gi, from this parameter space theta to d-dimensional Euclidean space Rd, such that for any two parameter theta and theta prime, and the ultimate policy pi theta or model theta, we can upper and lower bound the model estimation error under pi theta by some summation of bilinear structure. So here, P pi theta theta star is the distribution over observations if you execute policy pi theta in an environment parameterized by theta star. So theta star is the ground truth parameter. And this P pi theta theta prime is the distribution over observations when you execute policy pi theta in an environment parameterized by theta theta prime. And this condition says the model estimation error induced by using theta prime to generate observation distribution under pi theta is lower bounded by this bilinear structure divided by kappa. So you can think of this kappa as some relaxation. And the second condition says the model estimation error by executing policy pi theta in an environment parameterized by theta is upper bounded by this bilinear summation of bilinear structure. And finally, we have some normalization condition. So the high-level intuition is the model estimation error admits some special structure that is called summation of absolute values of independent bilinear functions. So if you are familiar with the definition of Bellman rank and witness rank, you can think of this condition as some kind of generalization of those conditions, because in the definition of Bellman rank and witness rank, you have a single inner product between two functions. However, we have here we have an additional double summation structure. So the condition is a little bit more general and can handle more problems beyond those previous conditions. And we can show both POM DPs and both observable POM DPs and decodable POM DPs, as well as well-conditioned PSRs satisfy this Thiel condition with moderate D, kappa, and B. And we can also show any problems that satisfy low witness rank will also satisfy this Thiel condition. Any question? Please.
PR Kuma, do you want to ask your question? You can unmute yourself.
Can you hear me now?
Yeah.
Yeah.
Okay. So if there is a policy, so in your first condition, Let's take theta and theta prime to be the same. Then if there is an optimal policy for theta prime, and then you're saying that you can recognize theta, distinguish theta prime and theta star. So you can separate, you don't have a closed loop identifiability problem. That's what you're saying.
It might not always, okay. It depends on your, okay, it depends on your feature mappings on F and G. It might be the case the inner product between these two feature mappings is 0. In that case, you cannot separate these two models.
But in that case, why do you need such a condition?
Well, why do I need such condition?
I mean, if you allow it to be 0, what's the value of that condition?
Okay, so if the inner product is 0, it basically means when you execute, okay, let's look at the second inequality. So if this inner product is 0, it basically means when you execute the optimal policy of theta, when you execute this pi theta, the distribution of observations under theta will be the same as the distribution under the ground truth parameter theta star. That means pi theta is optimal. It's also optimal for the ground truth environment on theta star. So that's good. So we don't need. So if this inner product is 0, we know we already found a good policy, and that's already good enough. And we don't need to really distinguish between theta and theta star. Yeah, they are different. So the second inequality is actually a weaker version of the first one. You can make them equal, but that will only strengthen the condition, right? So in the first inequality, we require theta and theta. So we allow theta and theta prime to be different.
So just so in the first one, if we have theta prime equal to theta star, then the left-hand side is 0, right?
Oh, in the first one, yeah, the left-hand side is is 0.
So theta prime equals theta star. So then the right, that says that all the inner products Fi, theta, and theta star have to be 0 for all theta?
Yeah, for all theta. Yeah, that means, yeah, because if you have the true parameter, yeah, if you already know the true parameters, then it should produce. You can reproduce the same distribution for every policy. Okay, so maybe it's better for me to put the definition of Bellman rank here, so we can make some analog. So if you recall the definition of Bellman rank, basically you have one function f, and you have another function g, and when you execute the greedy policy with respect to f, the Bellman error of G can be decomposed into some bilinear structure. So basically, you can replace the value function in Bellman rank by the model parameter theta here. You get something similar. Please. I can't hear you.
Oh, okay. No, so the thing is that the first condition, because it holds for all theta, theta prime, means that even if you do simple certainty equivalence, choose an estimate, choose the best policy, you'll always be getting information on theta star, always. So under those conditions, typically things are much easier.
Sorry, I don't quite understand your questions. So you are saying we know the optimal policy?
No. I'm saying that let theta prime be any estimate, okay, maximum likelihood, whatever, right? And
no, theta star is a ground truth parameter.
No, I understand. I'm saying let theta prime be, let us say, a maximum likelihood estimate, and let pi theta and 2 theta equal to theta prime. Then you're choosing some optimal policy corresponding to that. And then what it says is that the true system and the system that you think it is can always be distinguished. But anyway, we can take this offline. We can take this offline. Yeah.
I guess the right-hand side could be 0, right?
Yeah, it could be 0.
And then the total variation is 0. You can't actually tell the difference between these two distributions.
Yeah, if it is 0, yes.
Yeah.
So that would imply that Fi theta prime, Gj theta prime are orthogonal, which would have implications for the second inequality. Anyway, we can talk offline.
Oh, okay. Okay. That's basically all about this talk. And thank you for your time. And if you have any questions about the sale condition or the algorithm, we can talk about the details now.
All right, thank you. Thank you very much. Very nice talk.
Thank you.
So does the D here, is that the same D that you would get out of the witness rank, say, or the Bellman rank, or all of these things?
Yeah, it's this. Yeah, it's similar. So if
As in you.
Yeah, you can also. Yeah, you can also actually you can. So for witness rank, you can write it as a special case of sale condition, and the dimension is the same.
Yeah, I see. So in the U, that your D is always going to be less than or equal to the witness rank or whatever, or the Bellman rank, or all of these things.
Yeah, right.
Okay. And okay, maybe I can ask my question about the sparse linear bandits.
Yeah, right.
So there I had in mind that, okay, in a regret sense, you can get minimax squared SDT, and I guess there's some sample complexity equivalent, and you match that. But then there are also these situations where maybe you have some restricted isometry conditions about the action set or something like that. And what you should do is, maybe D is really large. So actually the best thing to do is to explore a lot and then even do explore, then exploit. And then you might get a bound that's like t to the 2/3 in a regret, but it only depends on S instead of D. And sometimes that's the right thing to do.
Right.
And I guess these optimistic algorithms are not doing this, but maybe you can fix it somehow. I don't know.
Yeah, I think you're completely right. We can get square root dst, but we can't get dimension independent bounds if we only use optimism.
Yeah. And can you get an analog of information-directed sampling that would fix this problem, but using, you know, this confidence set structure and?
That's a great question. So currently, there seem to be two different approaches for doing exploration. The first one is always be optimistic with respect to reward. And the second one is to greedily collect information like IDIs. I feel DEC is like some middle ground, is someone in the middle ground that combines both.
Yeah.
But
I guess IDS is also balancing these things, right? But it's sort of somehow Bayesian.
mm-hmm. Yeah, right. So information divided by regret.
Yeah.
I don't know. I haven't thought about that, and